You start a training run on a deep network, watch the loss tick down nicely for a while, and then it simply detonates. The number leaps to something astronomical, then reads nan, and every weight in your model is now garbage. This is the exploding gradient problem, and it is the mirror image of the vanishing gradient. It is a big part of why deep and recurrent networks were once notoriously hard to train, and understanding it explains exactly why clipping, careful initialization, and normalization became standard practice today. Let us pull it apart and see what is really going on. So what is really happening, and how do we stop it? Here it is side by side. When each layer's gradient factor is consistently bigger than 1, backpropagation multiplies these terms together layer after layer. That product grows exponentially with depth, so by the time the signal reaches the early layers, the gradient is astronomically large. A single update then hurls the weights to infinity, and the loss collapses into nan. A handful of well-established fixes keep the gradient bounded. Clipping caps its norm so no single update can blow up, careful initialization like Xavier, or he keeps each layer's signal scale near 1, and normalization layers hold activation steady across depth. Add residual connections and gated units like LSTMs, and an otherwise unstable run becomes a perfectly trainable one. How does a tiny problem snowball into total collapse? Watch the cascade unfold, layer by layer. It begins innocently. During backpropagation, a single layer produces a gradient factor that happens to be a little larger than 1. On its own, that is completely harmless, barely noticeable, just one layer nudging the signal slightly bigger as it passes through. But gradients do not travel through just one layer. The chain rule multiplies these factors together, layer by layer, all the way back through the network. In a deep model that is dozens of multiplications stacked one after another, each one compounding whatever came before it. And multiplication compounds fast. A factor slightly above 1, raised to the power of the depth, grows exponentially, so the gradient balloons to an enormous magnitude by the time it reaches the earliest layers. Recurrent networks make this far worse, reusing the same weights across every single time step. Finally, the dam breaks. That gigantic gradient drives one monstrous weight update, flinging the parameters to absurd values. The very next loss reads infinity or nan, and the run is dead. This entire collapse traces back to factors just slightly bigger than 1, compounded over depth. Strip it down and 3 ideas capture the whole problem. Gradients multiply and grow exponentially through depth. Backpropagation chains many factors together, and when they exceed 1, their product explodes with the number of layers, leaving the earliest layers with an astronomically large gradient. It is especially common in recurrent networks. Because they apply the same weights at every time step, that shared factor gets multiplied dozens or even hundreds of times over a long sequence, which is why RNNs were historically so prone to blowing up. It is tamed by a familiar toolkit. Gradient clipping caps the norm, careful initialization keeps per-layer signals near 1, normalization holds activation steady, and gated architectures like LSTMs plus residual connections give gradients a safer path. Alright, let us lock in what matters. The exploding gradient problem is a training failure where error signals grow uncontrollably as they propagate backward, sending weight updates to enormous values and the loss to infinity or nan. The cause is repeated multiplication. Backpropagation multiplies many per-layer terms through the chain rule, and when those terms exceed 1, their product grows exponentially with depth. Recurrent networks are especially vulnerable because the same weights are applied at every time step, multiplying dozens or even hundreds of times across a single long sequence until the gradient runs away completely. The fixes are well established: gradient clipping, careful initialization like Xavier or he, normalization layers, and residual or gated architectures. If untangling deep learning failures this way appeals to you, there is plenty more waiting over at standarity.com. Come explore with us.